Since this equation is about mixing two substances of different temperatures and finding the equilibrium temperature, we already know it's going to be about thermodynamics. And since we're mixing two temperatures and not worrying about the surroundings, we're going to basically look at a conservation of energy equation. So essentially, we start out saying that the heat energy, Q, lost by the T, because the T is hotter, is equal to the heat energy Q that's gained by the glass, G. And then from there, we can go ahead and use the appropriate formula for the heat, Q. Since both the cup and the tea are solid or liquid and incompressible, then we only have one particular equation that we can use for heat energy, and that is mc delta T. So we're going to go ahead and break this down into mc delta T by saying negative up here, m of the T, c of the T, and then we're just going to go ahead and break it down into the individual temperatures to common TF minus T naught of the T. And that's going to equal to the positive M of the glass, C of the glass. And again, breaking down into the changes in temperatures, TF, the common T final, minus T naught of the glass. Okay, now what we can do is we can go ahead and write down all the stuff that we know just to make sure that we have all the variables down. First of all, we're trying to find TF. That's our main goal. But just to make sure we have everything else, let's go ahead and list them out. The T naught of the glass is going to be 25 degrees Celsius. And yes, we're going to keep it in Celsius only because I want my answer to be in Celsius. So that's fine. If you want your answer in Kelvin, go ahead and convert this into Kelvin, convert this into Kelvin, and you'll get your TF in Kelvin. But since I want it in Celsius just for practical matters, then we'll keep this in Celsius. But again, it's your choice. We just have to be consistent throughout. The heat capacity of glass is, by looking up online, 840 joules per kilogram Kelvin. And yes, the unit is in terms of kilogram Kelvin. But here's a little tricky part. Because the change in temperature is, yes, the change in a Celsius unit temperature, it's the same as the change in a Kelvin unit temperature. Because if you go up 1 degree Celsius, you go up 1 degree Kelvin. So the change in temperature basically says that means that you can use Celsius and Kelvin interchangeably. So we won't really worry about the fact that this is a Kelvin unit quantity and this is a Celsius unit quantity. The change basically makes them the same. Okay. So keeping that in mind, the mass of the glass in kilograms is 0.150, and temperature of the tea is 95 degrees Celsius. Heat capacity of the tea is the same as the heat capacity of water, since tea is essentially water. This is just stuff that you want to, I guess, enlighten yourself with. It's going to be 4,186 joules per kilogram Kelvin. And again, we won't worry about the Kelvin because it's being up against the change in Celsius, which is the same as the change in Kelvin. So we can easily just cross off those things if we need to. Now, we don't know the mass of the tea, but we are given the volume. And since we know that tea is essentially water, we can say that T is the same as density times volume. So mass is density times volume. That's just because the density is mass divided by volume. The density of water is 1,000 kilograms per meter cubed. And the volume of the tea is, in terms of meters cubed, 0.0002 meters cubed. And you can see that the meters cubed cancels out, leaving a kilogram, and that is the unit of mass. So now that we know that we have all of the variables needed, let's go ahead and finally start isolating TF and working with the problem. Okay, so to write this out a little bit better, and I'm going to go ahead and use the variables again. I won't write out the numbers because that would just be too confusing from the get-go. The density of T times the volume of T, which is just covering up for the mass. times the heat capacity of T multiplied by temperature final plus density of T, volume of T, heat capacity of T, times temperature initial is equal to M of the glass, C of the glass, T final, minus M of the glass, C of the glass, T initial of the glass. Now let's go ahead and isolate T final by bringing this term to the left, bringing this term to the right, and getting rid of the all necessary negatives, and then isolating TF by putting the rest of the terms in a parentheses. So I guess the opposite of distributing out. So this actually comes out to be TF times M glass, C glass, plus rho T, VT, CT is equal to rho T, VT, CT, T naught of T, plus M glass, C glass, T naught of glass. Okay, now going up to greener pastures up here, let's go ahead and isolate T final once and for all. TF is thus equal to rho T, VT, CT, T naught of T, plus M glass, C glass, T naught of glass. All divided by what's in the parentheses over here to the left as we bring it over to the right. It's going to be M glass, C glass, plus rho T, VT, CT. And hopefully I wrote that all down right. Let me check real quickly. Looks right. So without plugging in all the numbers again, what I'm going to do is I'm going to just have you calculate it, but then I'll give you that 4 terms you see, 2 on the numerator, 2 on the denominator. It looks like the 2 numerator terms are going to be 79,534, and the unit is joules, plus 3,150 joules divided by 126 joules per degree Celsius plus 837.2 joules per degree Celsius. And the reason why I did degree Celsius, well, first of all, it's in Kelvin, right? But because this is used interchangeably as Celsius or Kelvin, I can go ahead and do the same thing here. So I changed it to a Celsius instead. And that means that this final temperature will be in Celsius, which is what you wanted anyway. Again, if you're more comfortable, just get everything in Kelvin and then transform into a Celsius unit after you're all done. It'll just take one more step, but it'll save the confusion. As you can see, the joules are going to all cancel out, leaving a Celsius to go on top. And voila, the final temperature is going to be 85 point, and I won't worry about significant figures right now, 0.843 degrees Celsius. And that is the answer.